All right, good morning, everyone. Hope we had a good conference so far. My name is Wenz, and what I'm about to talk for the next 60 minutes is actually a tale of failure. I started doing web application security in about 2000, 2001, and I've told this story before, so if you haven't seen it at previous NDCs, you may have heard that, but every year I think, okay, I do this for one more year, but then, the problem will have solved itself. I was young, I was cocky, and I was just wrong. Web security is as up-to-date and as pressing an issue as ever, and therefore great that all of you showed up today for a topic that I think is pretty satisfying. We're talking about the failures we as developers had when trying to battle attacks and trying to do proper web application security, and I prove this by showing that now even browser developers help us, because we alone, we messed it up, but browsers help us. So there are some built-in features in browsers that are either activated by default or can be activated with little effort to amend the security of our web application. So that's what these next 60 minutes will be about. I have a web browser here, and I have a page, and this page has a button. It says, "Do not do this." So what will I do? Exactly. Let's click on that. So it says, "Account deleted." I hope you can see it all right. That's a bad thing, so let's just close this browser tab and hope that this will never happen again today. I'd like to start with a pretty interesting website, which promises that they check the HTTP headers that a web server is using and sending, and then analyzing it whether it's kind of sound or not. So let's just use an arbitrary site. So how about ndc-london.com? And now that website is retrieved and it's scanned, and then we get a mark. Well, in that case, it's red and an F. Somewhere below, further below on that page, it says, well, an F is not, the end of the world, but there are some things that might be amended. And that's exactly what we'll do. So we'll talk about certain attacks, and I'm very aware that you hopefully know all of these attacks, and then we'll see how there might be techniques in the browser, by default or not by default, that help us battle those attacks. So that's what we're about to do. And then we'll come back to this at the end and see what could be made better on that website. All right. So I'd like to start with cross-site scripting. Cross-site scripting in the OWASP top 10, the list of the 10 most prominent security risks, which is released every 3 years, more or less. The new edition is only a few weeks away. And cross-site scripting is always, and has always been, in the top 3, and I expect nonetheless in the new edition. So this is a website that kind of enumerates CVEs and which kind of security vulnerability are behind that. And so this really shows that cross-site scripting, it goes up, it goes down. It goes down quite a bit at the end, but this is 2017, and if you look closely, that's more than 0, right? So only 3 weeks in, and we still had cross-site scripting vulnerabilities. So it still is a major threat. And for years, I've thought, well, cross-site scripting, cross-scripting is really, really bad. Because, the idea is that an attacker injects something in an HTTP response. Most of the time it's script code, but also HTML, for instance, can be dangerous. And if it's script code, it's executed in security context of the current page. The origin, we'll have a look at the origin in a bit, which allows essentially the injected JavaScript code to do anything that our JavaScript code, because it's our website, is about to do. So very, very bad thing, and so I always thought, okay, A, this is very bad, but B, it's so trivial to defend against cross-site scripting, especially if you're in an HTML context. So we have HTML, and then we have user-generated input, whatever, a search term. You enter on a website, in the search field a term, and the resulting page says, your search for XYZ has given us these results. So the XYZ is user-generated content because it comes from the user. And if you're in the HTML context, the only way to inject something like JavaScript code is to, well, change the context. How can we change the context? With angle brackets for tags, with single or double quotes for attribute values, and with the ampersand character for entities. If we escape those 5, then we are good. So this battles most of the attacks. Also, to even further decrease the attack surface, we might want to secure cookies, which is something we'll talk about. And we might want to use something rather new. Well, it's not really new, but rather new, called CSP. And we'll talk quite a bit about CSP later today. So actually, defense is trivial, but still, it's in the top 3 since I think the first OWASP top 10 came about in 2004 or even 2003. So almost 15 years now, and cross-site scripting is still one of the major threats. Why is that so? Well, there might be a myriad of reasons, but still, we need to defend against cross-site scripting, and there are several ways of doing so. First, I need to briefly discuss the actual impact of cross-site scripting, because it becomes important when we talk about countermeasures. The idea behind the security model of JavaScript is, yes, JavaScript does have a security model, and the security model has a name. It's the same origin policy. The same origin policy is based on the term origin, and the origin is defined by IETF. And the origin actually means the protocol or schema, the fully qualified domain name, and the port. If all of these 3 things match, then 2 things have the same origin. The origin in an HTML JavaScript context is the origin of the HTML page. So if you load JavaScript code on ndc-london.com, but the JavaScript code comes from whatever, Google CDN, because it's a JavaScript library hosted there, the origin of the JavaScript library is ndc-london.com, because ndc-london.com needs to run the code and maybe wants to modify the contents of the page. Thanks to the same origin policy, well, the origin must be ndc-london.com, otherwise that would not be possible. This does not apply, or the same origin policy does not apply to the src attribute. You can load code from anywhere, but the security context the JavaScript code runs in is the origin of the HTML page that loads the code. So just to make super clear what the same origin policy means, the first 3 URLs, they have the same origin because they're using HTTP, they're using port 80, and they're using example.com as the fully qualified domain name. The 7 down there, those, none of them share the same origin, because some of them have a different port like 8080 or a different protocol like HTTPS, or they have a different domain name altogether. All right. So that's why cross-site scripting is extremely bad and extremely dangerous. So what can we do against it? And actually the first, let's say, development team that tried to do something proactively against cross-site scripting from a browser point of view was surprisingly Microsoft. IE8, and I mean, nowadays, if you see IE8 at a customer site, or your customer tells you, well, we still use IE8, then maybe you're not too thrilled, let me put it that way. However, IE8, as bad as it may look today in comparison to modern browsers, IE8 introduced a lot of security features. So it kind of was a milestone, especially if you compare it to IE7 or even older versions. And what IE8 introduced is a cross-site scripting filter that was used for reflective cross-site scripting in order to battle it. There is no setting in IE that deactivates that filter. So it's there to protect users, and, well, users cannot disable that. Now, what happens if you kind of find out, well, the cross-site scripting filter, which turns up messages like this, kind of defeats the functionality of my web application? Well, there is an honest answer and, let's say, a more diplomatic answer. The honest answer is, you're doing something wrong, please refactor your app. But the more diplomatic answer as well, you may have found a very innovative way of doing code execution. If you really want to do that, you, as the developer, can disable that filter by sending an HTTP header. X acts as protection. The value of 1 enables it, but, well, it's enabled by default. 0 disables it, and there are other options too, but these are the basic options, right? So you can disable the cross-site scripting filter because thanks to the same origin policy, and that's why it is so important, thanks to the same origin policy, you as the person responsible for the web server, you are the one who is attacked because injected code runs in your origin, right? So that's something that's built in IE8. It's now also built in Webkit-Based browsers, so in Chrome and Safari, and Firefox is my favorite cross-site scripting testing browser because it does not have that filter built in. So whenever I try to find an XSS vector, I have to try it in Firefox because the other browsers might block it too. There are ways around that filter because the design principles of the filter was A, the filter has to be really fast, so no long analyzing of the input, and B, if possible, no false positives. Right? Because the filter is innate to give some additional protection to users, but the functionality of a website should still be there. So it's no excuse to not care about cross-site scripting. It's just an additional safeguard. I told you there would be several headers today. Some of them are quick wins. This one is, well, it's not even a quick win. It's a win that's already there because it's enabled by default, but just that you know. But against cross-site scripting, I think I have something better, which I'm quite excited about. It does come at a cost because the effectiveness of that measure depends on how well, let's say, well structured your web application is. But I think it might be something really interesting for you. It's called content security policy. You may have heard of that before, but let's just have a look what that's about. There are 3 versions currently of content security policy. Version 1, which is a W3C candidate recommendation since 2012, so over 4 years ago. There is a version 2, which happens to be also a W3C candidate recommendation from mid-2015, so it's 1.5 years old. And there's also version 3, which still is in editor's draft stage, so they're still working on that, but nothing is done yet. Pretty interesting. It's a feature that is supported by all major browsers, depending on the version number and depending on your definition of major. So content security policy 1 is is supported by all relevant browsers, also by current versions of IE, which I think is a pretty positive sign. And oops, sorry, where did I go? Sorry, my bad. I don't know why this moved, but let's just go back. There we go. So content security policy 1 is kind of supported by all browsers, starting with IE 11. It's a bit worse with content security policy version 2 because content security version 2 is offers really useful new features, as we'll see. However, the IE support is leaves a little bit to be desired. As you know, there will be another major update to Windows 10 this year, and this will also come with the new Edge browser version 15, internal version number. That one will have support of CSP2. So, in the not too distant future, all up-to-date browsers, let me put it that way, will have content security policy version 2 support. Up until now, all CSP2 features work best in Chrome and mostly in Firefox and also in Safari, but not in Microsoft browsers yet. But we'll see what that actually means in a bit. And well, version 3 is just a draft, so nothing special to mention here. The idea is this: the web server sends an HTTP header. And the HTTP header contains a policy that is telling the web browser how to, handle content on that page. There were different versions of headers, especially when content security policy was still in standardization phase, and it still is. You saw CSP 1 and 2, they are candidate recommendations. They are not recommendations, so they never reach the final status, but they're already working on the next version. So maybe it's, I don't know, something like Duke Nukem, right? So, eventually it will be released, eventually. And so there was the various different headers. Nowadays, on modern browsers, use the content security policy header. If you see some, blog posts or documentation with one of the older headers, that usually means that the documentation is outdated. One of the interesting features of content security policy version 2 is that in those cases where you cannot easily inject HTTP headers in the response from the server, you can also use a meta tag. With the meta tag, you can emulate some HTTP headers, including set cookie and others. And what you can also do now is set the content security policy header as is shown here, but only from CSP2. So in order to still support IE, if you're using CSP version 1, then sending HTTP header is probably the best way. And this is how content security policy looks like. We have a header, and then we have several directives. Directives are the keywords with the dash, and directives can have one or more values. So we have two directives here. Default src self, which essentially means, well, everything that is loaded from the web page, using the src attribute usually, must come from self, which is a content for the current origin. So basically, we can only load content from the current origin. Everything needs to come from our server. So if someone injects script src equals http://badserver.com/badscript.js, that is not loaded because the policy prevents it. And what I'm also doing here is that all the images on that page, they are loaded from static.example.com. So all the images must come from a specific server. Actually, let's have a look how that turns out. I have here a simple MVC-based application, and what I'm doing here is, if I call a specific page with a query string argument of CSP equals 1, in that case, I send a content security policy just default src self. So load everything from the current origin. And if I go to the CSP page, what we have here is we have a logo, so we have an image. We have a beautiful orange-colored bulleted list with two links, one to $CSP equals 1 and the other one not. And what do we also have? We have inline JavaScript code here, and we also have external JavaScript code here, so in an external file. The inline code, as you see here, alerts out inline, and the external JavaScript code does an AJAX request to an endpoint on the server, which returns external, and that text is then, printed out. Let's have a look in the browser how this looks like. So we go to our CSP example, and the page is loaded, and you see, okay, we get a JavaScript pop-up inline. Okay, fair enough. And then external worked. We have the orange list with the two links, and we have the NDC London logo. And what I'm doing now is I click on the first link, and if you're sitting on the front rows, you can see very small in the bottom left corner that we are calling the same page, but with CSP equals 1 appended to the URL. So we load the exactly same page, but this time with the header. And you see, we get the external pop-up. We did not get the internal pop-up, and when I click on that, the page renders, and somehow the color is gone. Something went really, really wrong here. Well, you probably are already guessing what's the problem. So what was deactivated? The color, which was an inline style, and the inline JavaScript code. So inline is considered dangerous. So by using a content security policy that includes policy for scripts, you disable inline markup like inline JavaScript and inline styles, which is, well, if you ask me, it's a good thing, but it really depends on how your page is set up. And if we go to developer tools and have a look, we see that in the console we have a couple of messages. Refuse to execute inline script. Refuse to apply inline style. So the content security policy prevented us from running that script and executing that code and displaying that style. And that's a good thing, because how does cross-site scripting work? Usually there are two attack vectors. One is someone injects script src equals badserver.com, as I explained. But, well, since we set our policy to only use content from our own origin, that code will not be run if content security policy is enabled. So that attack vector is closed if the browser supports content security policy. What's the second attack vector? The second attack vector is an attacker injecting inline JavaScript code. Inline JavaScript code is a bit trickier usually, right? Because it then seems to come from our server. There is no additional HTTP request to another server. However, as you see here, by default, inline script code is disabled when using content security policy. So that second attack vector is closed as well. So what's the only way to manage to do cross-site scripting now if CSP is enabled for an attacker? Well, you saw there was only one bit of code that was executed. And that bit of code was the file that resided on our server. So if an attacker manages to upload a JavaScript file to our server, then yes, cross-site scripting is still possible. However, if an attacker manages to upload a file to our server, cross-site scripting is probably the least of our problems. So I would say the cross-site scripting issue can be solved if we're using content security policy. So really, consider using that. I'll very briefly guide you through some of the features, real quick, of content security policy, and then give you some pointers how you can use content security policy, because there still is a catch, I have to tell you. All right, so there are several directives. We saw the default SRC directive, kind of the mother of all directives. There are more specific directives, which can be used to override the setting in default SRC. For instance, image SRC for images, script SRC for JavaScript, and style SRC for styles. There are also some changes in CSP2. I just put them here for reference, so when you have a look at the slides later, you have a very good overview. So these are the directives that exist, or at least most of the directives that exist, and they can have different values, and those values are, I think, noteworthy. There is something, you haven't seen this from me, right? Someone else told you that. You can use, the star sign, the asterisk, this kind of means everything, but you don't want to use this, right? Someone else told you that. You can use origin as we did, starting with CSP2, not only an origin, but also URI, so you can have pass in here. And then we have a couple of constants. Constants are delimited by single quotes. We already saw self, which means current origin. None is, I think, obvious. And then we have two more. And, usually when you have a standard, the standard shouldn't be opinionated, right? The standard should say what it is, but the standard, should not mock you. It does, because we have unsafe inline and unsafe eval. So this is like like if the standard was saying, okay, you can activate this and that, but well, then essentially you are kind of stupid. So really, this is I've never seen anything like this in the standard before. They were constantly like unsafe inline. So this is a bad idea inline, and this is a bad idea eval for evaluating code. So JavaScript eval function, function constructor, and stuff like that. So yes, you can activate inline styles and inline JavaScript code if you need it. Well, and sometimes you do need it. For instance, one of the biggest users of content security policy and one of the first users is Twitter. And if you look at the policy Twitter is using, because Twitter is loading so many assets and has so many different sites and people calling in from other domains and stuff like that, the Twitter security policy is extremely long and it's using unsafe inline. Well, and if you're using unsafe inline, this attack vector suddenly reappears, right? So you do gain something, but you do not gain much. So try to avoid it, but it's not always possible. So maybe some of you, someone asked in another talk yesterday who was still maintaining web forms applications, ASP.NET Web Forms, and some hands showed. ASP.NET Web Forms, they output quite a bit of inline JavaScript code and also inline styles. So with that, content security policy is difficult, but we will talk about kind of a potential remedy for that, because if you go to the browser again, and if we actually move this up a little bit so you can see that tiny bit better. What you can do is you can calculate the hash of the inline JavaScript code and put that in the policy. Right? So in your build process, you have a look at the JavaScript code, but you have to be super careful. You have to also take white space into account, character returns, etc. You calculate the hash, and then in the content security policy, you provide that hash value. So now the browser knows, hey, if there is code that has exactly that hash, I can execute it. And if you have code that never changes, you can also just use Chrome, have a look at that error message, and you have the hash that works. There are other options too. But still, it's kind of complicated, and that's a content security policy version 2 feature. So if you are using a browser that does not support that, then the browser doesn't support the hash here. All the browser sees is, oh, I cannot run any inline code, and then your code doesn't run. So that's probably not what you want to do. So, but that's an option you can consider using here for inline code, and there are other options too. But basically, that's what you want to do. Now, the problem with such a content security policy is, as you see here, if there is a violation of the policy. There are 2 reasons why there can be a violation of the content security policy. One reason is you forgot something. So let's just imagine you said you're using default SRC and you just say self, and then you're also adding the server name of the ad server where you display ads from, and of, let's say, Google Analytics, right? Because you're using Google Analytics and that code is loaded from another server, so you need to put that in the list too. But maybe the ad server script is loading in another resource from yet another server. If that's not in the content security policy list, that is not loaded. Your users might be happy because less ads, but still you probably want the ads to be displayed. So you really have to be careful and need to enumerate which kind of servers and which kind of origins you're using on your websites. There are tools for that as well, but the problem still is, if you mess something up, then you have a policy violation and maybe your website doesn't work as well. There's only one other reason for a policy violation. You have a security vulnerability and someone tries to exploit it. So actually that's a good policy violation. But how do you know about this policy violation? And that's a pretty amazing thing. There is an additional option called report URI. Your report URI is a directive where you provide a URI, and once there is a policy violation, an HTTP request is sent to the URI with all the info, which line, which file, which violation, which payload, etc. So you kind of get automatically informed when your policy is violated. The browser sends that to your endpoint. You have to create the endpoint yourself, or you can use a service like reporturi.to. It's .io. Sorry, it's the same. The gentleman behind that is the same one that also did the security header site I showed you at the beginning. That's still very nice, but yet you have a policy violation, which means that something is blocked which you maybe do not want. Unless it's an attack. So there is another thing, a header called Content Security Policy Report Only. It's the same thing as Content Security Policy, but the policy is not enforced. So the website runs as before, but if there's a violation, they inform you, or the browser informs you to be exact. So once you have a content security policy and you refactor your website that you do not use inline styles and do not use inline JavaScript code, then set up the policy and send it with the content security policy report only header. And then let it run for 2 weeks. And then see if anything is reported or not. So you can have a dry run, so to speak, of that policy without any functionality not working any longer on your website. I'm really excited about that technology. You should really consider using that, or at least evaluating that for your web application. I've had a lot of customers with implementing this, and really the attack surface just gets smaller, which really helps. Every little helps. All right, so that's a very quick dash through content security policy, but there's a little bit more. So one of the, let's assume there's a successful cross-site scripting attack. One of the attacks that happen quite often when cross-site scripting works is cookie hijacking, which means that cookies are somehow stolen. With cross-site scripting, it's easy. Another option is to steal those cookies in open networks, like here at the conference or depending which hotel you're staying, but usually it's open Wi-Fi, which basically means that everyone gets all the data in the network, but the driver on the network card just, picks the data that's for us. And of course, there are other drivers that, also have a look at the data that's not meant for us. And also little hardware dongles that enable that. I think at previous editions of the conference, some even tried that out. So be really super careful when you're using such an open Wi-Fi, just in general. The problem with the stolen cookie, of course, is that quite often such a cookie contains sensitive data, usually a session ID, and that session ID is used for authentication. Now we have to protect those cookies, and actually there are interesting ways. Cookies were invented by Netscape. HTTP, the protocol, is stateless, so doesn't remember anything, but Netscape thought, well, it should remember something. So in their specification, which is archived here, pretty interesting, the set cookie header had an option called secure. Secure means if this cookie is sent from the server to the client and the client chooses to store that cookie, to accept it, then the cookie is sent back with all subsequent requests to the same origin, but with the secure header only if the connection is done via HTTPS. This doesn't help against cross-site scripting, but it helps against open Wi-Fis, because in open Wi-Fi, if we have HTTPS and everything is configured correctly, then the data is encrypted. The data is encrypted before even HTTP headers are being sent, so we are safe there. The other thing is that, again, Microsoft invented something, surprisingly, and the other browser developers, they chimed in and were also using that, is another cookie option called HTTP only. HTTP only is a setting you see when you create cookies with C# and ASP.NET. It's also an option in web.config, which you can set for session cookies, and I do recommend you do that. And what HTTP only does is, this cookie is only sent via an HTTP connection, and together with secure, only via an HTTPS connection. What does that mean? Well, JavaScript has access to cookies too. And if you have cross-site scripting and can inject JavaScript code, then those cookies, well, might be accessible to the attacker's JavaScript code. If we set HTTP only, then JavaScript does not see that cookies. At least that's what the specification says. It's not completely correct, but it's close enough. There is one workaround, and I think we have the time. I'll show you that workaround. I have here the tool I'm only resting, which is like Postman, where you can send HTTP requests, and I have an IIS here on my local machine. And what you probably can see here is I have a URL, and I can set a method, I can set headers. So let's just say I emulate a request to the server, and I send something with it automatically. Cookie, whatever, session ID equals ABC123. And if someone manages to inject dangerous JavaScript code, they can do an AJAX request to our server, right? Because that's what JavaScript is allowed to do. And instead of sending a GET request, they may want to send a trace request. And if we send a trace request, this is what we get back. The trace request is a debugging feature. So the trace request sends back all the HTTP headers we have been sending to the server, including line 4, the cookie header. So even if a cookie is secured by HTTP only, if JavaScript can send a trace request to the server, JavaScript gets access to that cookie. Now, why is this? This is called cross-site tracing, by the way. Why is this an attack that's, well, not very common and actually not very well known? Because, well, I had to configure IIS that it accepts trace requests. Usually trace requests are disabled for most web servers, but you might want to check your own web server if trace is disabled. If not, disable it because, well, you don't need it. The only person needing trace for HTTP is the attacker for that specific attack vector, so you can easily disable it. So we can kind of protect cookies by using secure and HTTP only and disabling trace. But there's even something better, because HTTPS is key, and as you know, browser versions that are, I think the Chrome version that comes out in a couple of weeks, kind of errors out when you have, for instance, a login form that's not using HTTPS. So using HTTPS is getting more and more important, so maybe you want to enforce HTTPS. And there are ways of doing it. One standard here is HSTS, HTTP Strict Transfer Security, which works in the following fashion. So you send an HTTP request to the server with HTTP, so no HTTPS, and the server wants to make sure that you never do that again. The server then can send a strict transfer security HTTP header with a couple of options. And this does two things. First of all, the connection is switched to HTTPS. And secondly, that's one of the prerequisites actually. But what then happens is the browser remembers that. So whenever you go to, let's say ndclondon.com had this header, whenever the browser goes to http://ndclondon.com and you type this in and press enter, then the browser sends a request to https ndclondon.com. So no more attempts of sending unencrypted requests to that server as long as the max age timeout is not met. So a year or two is, I think, a good idea. Modern browsers do have a preload list, so a list of domains that kind of signed up for being preloaded in that list. And it's not just the big domains in there are also smaller ones too. And there are several steps involved in order to become part of that list. What you need to do is you have to do a redirection from HTTP to HTTPS. You have to use HTTPS on all subdomains. And you have to send the strict transfer security header and add preload at the end. And once you've all done this, then you go to a special website. And on that website, you just put your domain name in here, check status and eligibility, and then eventually your domain, if you did everything correctly, will be part of that list, right? So everyone who's using a browser, even the first time they try to go to, let's say, http ndclondon.com, they will use HTTPS because the preload list instructed them to do so. You have to add the preloads at the end until you're part of that list, so it's impossible that some other website or competitor kind of puts you on the list without your knowledge, right? So you have to actively do that. Really, really great, because then really 0 requests are being sent with HTTP to your websites any longer, and also no mixed content warnings, etc. So this I think is a good value. This should be approximately 2 years, which is pretty nice. So that's a kind of a new standard, but we talked about content security policy already, and there's also a way of enforcing HTTPS with content security policy. There is a new directive called Update Insecure Requests. It's not part of a content security policy standard. It's a different standard, but it kind of, joins in with content security policy. And what this does is exactly what the name says. It upgrades insecure requests. So let's just imagine you have this policy, and on your page there is a link to HTTP, whatever, ndclondon.com. Then if the user clicks on it, it goes to HTTPS, ndclondon.com. This is a feature that's currently only supported by Chrome and Firefox. So it doesn't always make much sense to send out that header if the browser doesn't support it. However, for instance, Edge has this feature as under consideration, so it might eventually come, but it will not come with the next Windows 10 update. However, browsers that do support this feature, when sending an HTTP request, they send along, as you see here, a header with the HTTP request. Upgrade insecure requests value is 1. And if you get that header, you then, as the server in turn, could send out content security policy update insecure requests in order to facilitate that feature for your web application. And finally, since we've been talking so much about secure connections and HTTPS, there's one more thing, and that's public key pinning. The idea here is the following. Just imagine, you buy a certificate from some authority, and then that one gets hacked. That happened before, right? So someone might be able to issue a new SSL certificate or TLS certificate in your domain's name, which, well, is not that good, right? What you can do is to use HTTP public key pinning. The header is called public key pins, and public key pins then expects a list of, well, of the hashes of cryptographic identities which you trust. So, for instance, that could be the hash of your certificate, and, well, either you buy a backup certificate as well, so, because just putting in one usually is not enough. So either you buy a certain certificate, or you do a sign-in request and use that hash. So if your certificate, whatever, expires or something's wrong with that, you still have the sign-in request and then can set up a new certificate. So you do public key pins, you provide the hash value. That's usually where I mess up, because I always have some issues, doing the calculations right for that hash. But eventually I succeed. Even I succeed. And this is good for, I guess, 1 month. And, well, then you send the header, and then the browser refuses the connection if the hash of the certificate doesn't match. Again, the issue is, what if you mess up? Because then no one can use your website any longer. So there is also a test node. It's the same as with content security policy. The header is then called public key pins report only. And again, same as content security policy, there is a report URI option. It will be renamed in a few years maybe, but currently it's report URI. And when, well, the browser sends, if there's a violation, a request with the violation information to the URL you provide. However, still your website continues to work. Remember the report URI.io service I briefly mentioned before? That one works for this kind of reports as well. All right. So these were all options of, getting secure connections, and there are other attacks I would like to talk about towards the end. And one very common attack is cross-site request forgery. Cross-request forgery, once again, if we look at the numbers of vulnerabilities by type in year, so, I mean, this kind of went up pretty high, and for some reason, it went down significantly in 2016. And, well, again, 2017, but we are far above 0 3 weeks in. But still, so it's a problem. It's a problem that is not as, let's say, prominent or widespread as cross-site scripting. Not necessarily because the issue does not exist that much, but cross-site scripting is easy to find, easy to detect, and easy to prove. Cross-site request forgery sometimes, requires a bit more effort. Also, for cross-site request forgery, what we need to know is that many frameworks now come with cross-site request forgery protection. Sometimes you have to enable it, but still, more and more systems do have that. Now, I don't want to talk about cross-site request forgery in particular, because there is no HTTP header that can protect us from that. But I'd like to talk about another, let's say, version of that. A cross-site request forgery usually means the user doesn't do anything. But there is also a version of cross-site request forgery where the user does something. And the version I want to talk about is called clickjacking. So this is a screenshot from Facebook. And I didn't do anything with that, right? So I censored a word here, but apart from that, that's a true screenshot. And I know that person, and let me just say I was pretty surprised that I saw this, right? Of course, I mean, you gotta do what you gotta do, so I went on researching. So I had a closer look on that page referenced here, and I have the page here with me, actually. No, I almost have the page here with me, but it's in a bit of a different fashion. So this kind of is the page, right? And so when you go to the page, you see a link here saying click here. And again, front rows might see that, bottom left corner, this goes to google.com, and there is 0 JavaScript on that page, right? So I wouldn't trick you, at least not that cheaply. The problem is if I click here, then it says account deleted. Remember that? Wasn't there this button, do not do this? What's wrong here? What's wrong here? Well, actually, let's have a look at the page. I'm a bit confused. So we have here some CSS. I don't know CSS very well. And we have here a link. And, well, the scroll bar is suspiciously small. But still, I mean, it's just a link, right? So let's maybe change CSS a little bit, reload that page. And what you see now is that on that page, we had an iframe. And the iframe contained the page with the button. But we use CSS that the iframe doesn't show, so we wanted to click on the link, but instead we clicked on the button. That's the layman's version of a clickjacking demo. There are much more elaborate versions out there that are used by attackers, where there's JavaScript code that moves the iframe to where your mouse pointer is, right? So wherever you click, the button's already there. And what was happening with my friend Stefan here is he was kind of informed of that page, and when he went to that page, he saw a button, click here to whatever, get access. But when he clicked on that button, and I saw that, when I loaded the page and had a closer look, he clicked on the Facebook like button, which was hidden in an iframe underneath that button. And this is really bad. It's called clickjacking. I mean, cross-site request forgery, it's a common attack, common countermeasures. But here, the user is actually clicking on the button, right? The user is clicking on that button. What can you do? You cannot forbid people from clicking on a button. What's the prerequisite for that attack? The prerequisite for that attack is, I mean, just imagine, the button is kind of a metaphor for any button that has consequences in your web applications. For instance, add an account, delete an account, make someone an administrator, buy something. So it's usually a different page that is loaded in an iframe. So what's the prerequisite? The attacker controls the outer page and tries to hack the inner page. The prerequisite is that the inner page can be loaded in an iframe. Well, the older people in the room probably remember the 1990s. Can you? Well, if you remember the 1990s, you haven't been there, as they say. But in general, in the 1990s, we had frames. And people were using frames to steal content from other pages and load them in one of the frames. Some of you remember, I see you nodding. And what did we do back then? Well, there were some JavaScript snippets, frame busters, and those frame busters tried to detect, okay, am I in a frame? If so, whatever, redirect. So if you still have the code you wrote in 1995, then you might, go to your archives and use that code again. But, well, it's 2017, so we have better measures. Once again, there was something introduced by, surprisingly, IE8, an HTTP header called xFrameOptions. xFrameOptions is a header telling the browser, and all browsers nowadays support it, okay, either deny this page cannot be displayed in an iframe, or same origin. This page can be displayed in an iframe, but only if the outer page has the same origin as the inner page. Means we can frame our own content, we cannot be framed by someone else. I have a very simple example here. I have two iframes here, and both load the same page. It's a page that just says frame data or something like that. However, the second one uses setHeader equals 1, and the implementation on the server sends the xFrameOptions header with value deny once setHeader equals 1 is there. So when I load that page, we'll get two iframes loading the same URL, the same document, but the right iframe, will have the xFrameOptions header, and that's how that looks like. So you see, the second iframe remains empty. If you're using IE, you even get one of these pretty error messages, so even more embarrassing. And that's what I call a quick win, right? So if you have a page where one click has an effect, or maybe even 2 clicks, if you do good kind of social engineering or the clickjacking attack is executed well, even several clicks shouldn't be a problem. But if you have a page where one click does something, and you have a user that authenticated and that Clickjacking does something, just use xframe options deny. And you close the attack vector, and actually there's no really good alternative, right? Because, I mean, you cannot prevent the user from clicking, but you can prevent the browser from loading. Content security policy version 2 also has a directive that prevents this, that has the same effect. So eventually, the xframe options header, as you see, it starts with an X, so it's kind of preliminary header, will be replaced by the content security policy directive. However, as of now, it's CSP2. There is no IE support for it. So we have to stick with xframe options because that works back to IE8. And it's actually the only difference. All right. And, one more thing. It's a smaller aspect, but still. Some browsers, especially IE and Chrome, they try to guess what kind of file type we have. Now, there is an established mechanism for that, and the established mechanism is having a look at the MIME type, right? So the server sends content type HTTP header, and that content type HTTP header rules, usually. However, IE and Chrome sometimes want to be more clever than the web server, so they have a look at those files and ignore the content type header if they think, oh, that's not HTML, that's something else. Well, if you think about, drive-by downloads, right, or if there's a way that users can upload content, and you give that content, whatever, a file extension, and that file extensions trigger the content type. However, the content of the file looks like something else. Maybe someone could, for instance, inject JavaScript code. Imagine you allow the upload of text files and there's JavaScript code in it, and then an overzealous browser considers, well, it's JavaScript code, let's just execute it for good measure. This can be avoided with the X content type options header. Not very well known, it only has one value, no sniff, right? So browser, do not try to sniff the content, trust the content type setting. Of course, the prerequisite here is that you do have a content type setting. That's correct. Well, let's go back where we started and have a look at the scan result for a conference website. And what were they complaining? There's no content security policy. And well, content security policy is great and effective, but it takes time and effort to create a good content security policy. And of course, the website needs to be prepared to that. So, I mean, it's marked as red here, but is this a problem? I don't know. I would love to see a content security policy, but well, if you don't have one, consider using one. But if your considerations turn to the decision, no, we do not want one, then, well, that's the decision. We have xframe options, which is missing here. We do not have XSS protection. As I told you, it's enabled by default, but we can also enforce it if there's a group policy eventually still disabling that feature. So we can specifically send this. And also X content type options is the one we discussed last. Still, is this now a problem? Because, well, conference website has an F. Well, it really depends. The conference website is not it sounds the wrong way, a precious website. What I mean is, of course, it's an important website, but it doesn't process any user data. There are no actions on that website that do something. Why? Because ticket sales is done on another site, right? And the ticket sales website has a better score. But really, again, on the conference website, you cannot do anything. So clickjacking is not an option. It displays information. Since it displays information and doesn't accept user inputs, cross-site scripting attack surface is rather minimal. And there's also no need for content security policy, more or less, right? So once again, there is no 100% security, right? We should try as hard as possible, but at the end of the day, it's all risk management. And the risk management assessment for a conference website says, well, there's no real risk involved here. The risk is, if there's a risk involved, it's where the conference tickets are sold, right? And so always take all of this with a grain of salt, identify what are your risks, and then talk about remedies. And as we could see here, many of those remedies, many of those HTTP headers, they're extremely effective, and many of them are cheap to use. It takes minimal effort to use them, but you have maximum gain. And with that, that's all I had. Thanks for coming. Enjoy the rest of the conference. Have a good day. Thank you.